Hello, everybody. Welcome to Chapter 2, Atoms, Molecules, and Ions. I'm Mr. Koker, and this is for I'm at Seymour High School AP Chemistry. We're looking at Zumdahl 10th edition, Chapter 2. Before watching this, you should read pages 35 through 65. This chapter is titled Atoms, Molecules, and Ions. These are the three primary particles that make up the atomic level of chemistry. Some things are made of individual identical atoms, like copper. Copper metal would be copper atoms. Other substances have molecules at their basic level. Water is made up of molecules. Other substances have ions at their basic level, such as sodium chloride. Here we show the formation of molecules of hydrogen from atoms. When you have two identical atoms of hydrogen, they can share electrons and make a single bond and form H2. We also show the formation of sodium chloride from sodium and chlorine atoms. Sodium atom starts out with 11 protons and 11 electrons, and chlorine atom starts out with 17 protons and 17 electrons. After a transfer of an electron from sodium to chlorine, the sodium ion, which as you notice has shrunk in size, has only 10 electrons now and only 2 energy levels instead of 3. And the chlorine atom has gained an electron to fill its p sublevel and now has 8 valence electrons and 18 total electrons. And it is now larger than the sodium. So the atoms, chlorine was actually smaller than sodium, but the ions, chloride is actually larger than sodium ion. So sodium and chlorine were walking down the street one day, and sodium said to chlorine, "I think I lost an electron." Chloride said, "Are you positive?" Notice the sodium and chloride ions fit together into a pattern, a crystal, a 3D ionic crystal pattern with alternating positives and negatives that maximizes attractions and minimizes repulsions and creates a cubic crystal. When you look at a grain of salt through a microscope or a magnifying glass, you would see that the salt grains are actually little cubes. Okay, if we look back at the early history of chemistry, chemistry has been practiced for thousands of years, beginning with the processing of metal ores. Early man would have taken metal ores out of the ground and heated them up to process them into pure metals. One of the easiest metals to do that was copper. And so we have the Copper Age, followed by the Bronze Age, followed by the Iron Age. Basically, easier and easier to make those metals from their ores. We know that early on that man was making embalming fluids. They were producing vinegar from various grape juice. They were making wine from grape juice. So chemistry has been going on for a while. Some of the earliest philosophers or scientists to try to explain the nature of matter were the early Greeks. And you have some of the Greeks, Leucippus and Democritus, that believed that the fundamental particle of matter at the very tiniest level was an atom or something that was indivisible, not invisible, but rather the smallest particle, that if you were to cut things in half over and over again, that eventually you'd get down to a smallest particle that could no longer be divided. Other Greeks thought it was important to think of matter as being made of elements like earth and air and fire, water. So they believed that elements were the way to think about it. So it's interesting that today we still believe in both of these terms as good ways to describe matter. that we have at the smallest level atoms, and that atoms make up the elements that we know on the periodic table. After the early Greeks, we had a period of alchemy. Much of the theories of alchemy were proved to be untrue and didn't really work. But the alchemists were excellent experimental scientists, and they did develop many of the techniques that we now use today in chemistry. George Bauer was a metallurgist, and Paracelsus was a pharmacist or a doctor, and they made some advances in experimental chemistry. Robert Boyle is considered one of the first quantitative chemists, in that he took measurements, and those measurements were not just haphazard, they were carefully, results were measured. Boyle, of course, is famous for the Boyle's Law, involving the pressure and volume of gases, but he also wrote an early chemistry textbook called The Skeptical Chemist. Much of the 1700s was used by chemists to debate the nature of combustion. One of the mistaken ideas was that combustion was the release of phlogiston, and that substances released phlogiston when they burned. And so something like coal or wood had a lot of phlogiston in it, and that's why it could burn. It was later shown by Lavoisier that oxygen is the key to combustion, and it's actually the combination of oxygen with fuel that generates combustion. So Lavoisier was one of the early chemists to lead us to our current understanding. Many people consider him the father of modern chemistry. He's quite famous for his law of conservation of mass, that mass is neither created nor destroyed in a chemical reaction. In his work as a tax collector for the French government, he probably had access to some of the best equipment for measuring mass, and he was able to show that in a closed container that you could perform a chemical reaction and the mass would not change. So his balances were able to detect that mass did not change in a chemical reaction. Unfortunately, we lost Lavoisier. His connection with the French government led to his beheading during the French Revolution. So we lost a bright young scientist. Many people believe that his wife, who was also very intelligent, helped him with many of his experiments and with many of his ideas about chemistry. Lavoisier was also responsible for the current understanding of combustion theory, that it was the addition of oxygen to combustible materials that allowed them to burn. Besides the law of conservation of mass, advances in technology for measuring mass led Proust in the late 1700s to develop his law of definite proportions, that a given compound always contains exactly the same proportion of elements by mass. Based on these two, Dalton began to think about the possible existence of atoms. As he looked at the proportions of elements by mass, he also noted that when two elements form a series of compounds, or more than one compound possible from the same two elements, that the ratio of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. So for example, carbon dioxide and carbon monoxide, if you look at the relative amounts of oxygen and carbon in them, their ratios can be reduced to small whole numbers. So this is illustrated in example 2.1, page 39, so I'd suggest looking at that to see the law of multiple proportions. So we have these patterns. Seems that elements are able to somehow do math, or that they have certain proportions in which they mix and combine. So these patterns must have a reason. So we have these laws. Now, what is it that explains the laws? We need a theory, and that's where John Dalton stated in 1808, his new system of chemical philosophy, Dalton's atomic theory, that all matter consists of individual particles called atoms, that atoms of the same element are similar in shape and mass but different from the atoms of other elements, that atoms cannot be created or destroyed, and that these atoms of different elements may combine with each other in fixed, simple whole number ratios to form compounds. They're not technically compound atoms, but more like molecules or ionic crystals. So then much of the 1800s was spent combining elements together and looking at what ratios they combine and speculating about what the masses of the atoms must be. One particular advance in the early 1800s that helped with this experimental task was that Gay-Lussac noticed that when gases combine, when gas volumes combine, that they react in whole number ratios. So notice the similarity to Dalton's atomic theory that compounds have whole number ratios. And so the idea that equal volumes of gases react in whole number ratios, for example, 2 volumes of hydrogen react with 1 volume of oxygen to make 2 volumes of water vapor. Notice the 2 to 1 to 2 ratio, the whole number ratios that the gases react in. This was believed to be that the atoms or molecules were in fact reacting in those whole number ratios. That's based on Avogadro's hypothesis that because gases have quite a bit of space between their particles, that equal volumes of different gases contain the same number of particles. Now you might think, why would small particles fit in the same size box with the same number of particles in a box as large particles? But think about the desks in the classroom. We have 30 desks in the chemistry classroom, and it can hold 30 small freshmen or 30 large seniors. The same desks hold the same number of students regardless of whether those students are small or large. And that's because the spacing between the desks is really what fits the desks in the room, not the size of the people that sit in the desks. And so it's kind of like the molecules in a container always have the same spacing at the same temperature and pressure regardless of whether they're small molecules or large. And that's because 99.9% of a gas is in fact the empty space. And so the size of the particles is negligible compared to the size of the space between the particles. So now that we have spent the 1800s trying to figure out as much as we can about the elements, the 1900s were spent trying to figure out about the atoms that make up those elements and what the structure of those atoms were. And so in the late 1800s, J.J. Thomson, using his cathode ray tube, leads to the discovery of the electron, and he measures its mass to charge ratio. Thomson was the first one to develop a model of the atom. It's an incorrect model called the plum pudding model, but in his first theory of the atom was positively charged matter with electrons sprinkled about, kind of like plums in a pudding or chocolate chips in a chocolate chip cookie. Millikan was able, with his oil drop experiment, to measure the charge of the electron, and then Henri Becquerel discovers radioactivity and figures out that radioactivity has 3 types, alpha, beta, and gamma. So we're learning more and more about the particles that make up the atom. And then in the early 1900s, Rutherford's gold foil experiment leads to realizing that alpha particles can bounce off of gold, leads him to theorize the existence of the nucleus of the atom. And so we have the nuclear model of the atom. So we went from J.J. Thomson being the first to discover that the atom had parts to Rutherford's gold foil experiment leading to our current understanding of a nuclear model of an atom. And that all happened in a very short time, about 20 years, from J.J. Thomson to Rutherford. Now, our modern view of the atom, uh, we're only going to introduce it here, and we'll go into more detail in later chapters. But we believe that the atom has a very tiny nucleus, something like 10 to the minus 13 centimeters in size, and that the electrons move about that nucleus at distances of about 10 to the minus 8 centimeters away in something we call the cloud of electrons. The atom has three different types of components: protons, positively charged; neutrons, neutrally charged; and electrons that are negatively charged. Most of the mass of the atom is the protons and the neutrons, and they are held together by strong nuclear forces in the nucleus. But the chemical properties are mainly determined by the number of electrons and their arrangement into energy levels and sublevels. And so the chemistry is mainly due to valence electrons, the electrons in the outermost level. Because of electrical neutrality, an atom is going to have the same number of protons and electrons if it's a neutral atom. So if an atom such as aluminum is element number 13, its atomic number 13 tells us the number of protons. And because the atom is a neutral atom, unless it's lost or gained electrons, it should also have 13 electrons. That's how it stays neutral. So 13 protons and 13 electrons. Now the mass number of aluminum is 27, and that should be the sum of the protons and the neutrons, because the mass of the electron is negligible. So with a total number of protons and neutrons of 27, and 13 of those 27 being protons, that leaves you with 14 neutrons in the isotope aluminum 27. So you should review from Chem 1 how to count the protons, neutrons, electrons that make up an atom. Try example 2.2, page 48, to reinforce that skill. Okay, so that's atoms. Now moving on to molecules and ions. Two nonmetal atoms, because they have similar pull for electrons, will actually end up sharing electrons. We see that in water. Water is made up of oxygen atoms and hydrogen atoms. Oxygen and hydrogen are both nonmetals, and they share a pair of electrons to make a single bond between the O and the H. And then the other H also shares with oxygen to make another single bond. So HOH in a bent shape, it turns out. We'll learn about shapes of molecules later. HOH, or water, is a molecule. So three atoms covalently bonded, two of them hydrogen, one of them oxygen, is a molecule of water. And so a set of atoms bonded together covalently is called a molecule. This structural formula is showing how the atoms fit together. So we'd call that maybe a Lewis structure. We also have ball and stick figures that are often used to show shapes. And then you might actually show the shape with a space-filling model, which we see as the third molecule of water on the right side as you move from top to bottom. So a space-filling model is probably the most realistic because it shows the atoms as clouds of electrons, and those clouds are overlapping. Atoms really don't fit together with sticks between them or lines between them. Atoms fit together by sharing electrons, which means they overlap their clouds. So the space-filling model is probably the most realistic, or most similar to real world. We also should be talking about ions. The other way that atoms can bond is by gaining and losing electrons. The loss of electrons forms a cation, or a positive ion, pussycats. The cation word has a T in the center, which sort of looks like a positive sign or a plus sign, and so that's one way of thinking of cation as being positive. So something like sodium can lose an electron and become positively charged because now its protons outnumber its electrons. Its positive protons outnumber its negative electrons. The atom that gains electrons, the anion, becomes negatively charged depending on how many electrons it gains. And that would be what happens with chloride. Now that they are positive and negative, they have an attraction because opposites attract, and you form an ionic bond. If that ionic bond fits together into a large crystal, you have an ionic solid packed together in a crystal pattern. We also have groups of atoms that are covalently bonded together that can also have a charge, such as the 3 O's and the carbon, shown here in the bottom right-hand corner with a 2- charge. We call those polyatomic ions. You might remember those from Chem 1 and the fun of getting to memorize the polyatomic cations, anions, and cations. Okay, a quick introduction to the periodic table. We see the first column of the periodic table is called the alkali metals. Usually we don't include hydrogen in the alkali metals. We throw it in with the nonmetals. We have the alkaline earth metals in the second column of the periodic table. And then we have the transition metals, which are filling up the D block in the center of the periodic table. The F blocks down below are the lanthanides and the actinides. We have our post-transition metals shown here in gray. We have aluminum, which is really kind of metallic as they come. So typically we don't include aluminum with the metalloids. We have the metalloids, which are along the diagonal, which runs from boron down to astatine. Metalloids have properties physically and chemical, kind of between metals and nonmetals. We have our nonmetals, which are in the upper right-hand corner of the table. Within the nonmetals, you should probably know that the last column from the right is called the halogens, and that the noble gases are the final column in the periodic table. Columns in the table tend to have similar properties, and we have some predictable patterns in the changes of the properties of atoms as we go along the rows of the periodic table. The columns of the table are called groups or family. The rows are called periods or series. Finally, and this will probably be the biggest skill in Chapter 2, and that is the ability to name simple compounds. Naming compounds is a bit complex, but you did practice it quite a bit in Chem 1 and some more with the summer assignment. But just briefly, to kind of take you through naming a compound, naming a simple compound, the first question is to look at how many different elements are present in the compound. There should be at least 2. So let's start with the very, very simplest, which would be 2. We would call it a binary compound. If the binary compound contains a metal, then we're going to, if a metal is present, then we're going to have an ionic compound. So we're going to name the metal first, and we're going to name the negative ion, the nonmetal ion, second. So we have something such as sodium chloride. Sodium's a metal, chlorine's a nonmetal, sodium chloride. Don't forget to change the name of the nonmetal by adding IDE. The number of electrons they lose or gain depends on their column in the table and how many valence electrons the metal has to lose and how many valence electrons the nonmetal needs to gain to become a stable filled p sublevel or stable octet. So you can predict the formula by looking at how many electrons something loses and how many electrons something gains, or just thinking about the columns of the table having certain charges. Now that kind of breaks down in the middle of the table, because in the middle of the table you can't really predict the charge of a metal ion. So that's where we bring in the Roman numerals, such as iron 3 or iron 2. Iron 3 has a +3 charge, and iron 2 has a +2 charge. So the charges of the positives and negatives need to balance. So quick example, if I say calcium chloride, calcium is in the second column, it's a +2 ion. Chlorine is in the halogen group, it's a -1 ion. So in order for a +2 calcium and a -1 chloride to balance, you would need 2 of the chloride, 2 of the -1 to balance the +2, so it would be CaCl2. If I had iron 3 oxide, iron 3 is Fe+3, oxide is O-2, so to get +3 and -2 to come out even, you'd need 2 +3s and 3 -2s, so it's Fe2O3. Don't forget the subscripts are how we tell how many of each ion fit together to make the formula. You might find that you have two elements. You have a binary compound, but they're both nonmetals. So being nonmetals are going to be covalently bonded, so you can't predict their formula from their charges. So as a result, you have to use prefixes to explain the number of each nonmetal that make up the compound. So for example, carbon dioxide would be 1 carbon atom and 2 oxygen atoms, so the formula would be CO2. So those would be in these figures, like figure 2.22, the type 3, the type 2, and the type 1 binary compound. Now, if you don't have a binary compound, if you have 3 or more elements in your compound, then you're probably one of the ions, either ammonium or one of the negative ions, is going to be a polyatomic ion. So with that, we have to include the name of the polyatomic ion in the name of the compound, such as iron 3 carbonate. So iron 3 carbonate would be Fe+3, and carbonate would be CO3 -2. So to get that to balance, you would need 2 Fe+3s and 3 CO3s. Now it's a little awkward to put a 3 on CO3, so one way we get around that is by putting the polyatomic ion in parentheses if we need to put a subscript like 3 or 2 after it. So the parentheses basically means, just like in math, that you are multiplying everything in the parentheses by that subscript. All right. Finally, there's also naming acids. If you're naming acids, then you want to look at what the negative ion is in the acid. For example, a simple acid like a binary acid, HCl, we have H and Cl, and Cl is a chloride. So HCl, the ide ions form the hydroic acids, and so HCl would be hydrochloric. If your negative ion is a polyatomic ion, if it ends in ate, we don't use a prefix, but we use a suffix -ic in place of the suffix ate. So sulfate would give us sulfuric acid. Phosphate would give you phosphoric acid. If your suffix is "ite," then you replace the "ite" with "ous." And so sulfite, sulfurous acid, phosphite, phosphorus acid. And so you simply have to look at the suffix to determine the name of the acid. Interactive examples 2.3 through 2.9, pages 54 through 62, can be used to illustrate how to name and write formulas for compounds. And that will be a large amount of your practice this week, is going to be naming simple compounds and naming acids and ionic compounds.